We now know how to extend a premeasure to a fully fledged measure on any sigma-finite premeasure space. We also have constructed a large family of premeasures, at least on the real line. And so now we have a large family of measures to work with. Let's look at those a little bit. In this course, we will principally be interested in the Borel sigma field as our basic sigma field for probability measures on the real line and more generally on metric spaces. In fact, on the real line, those Borel measures can be characterized very nicely, at least those that are locally finite. A Borel measure on the real line is called a Radon measure if it is finite on all compact intervals. Now, more generally, the term Radon measure refers to Borel measures on any topological space that are locally finite. They take finite values on all compact sets and additionally satisfy some regularity conditions. If you want to look it up, it means outer regularity and inner regularity. It turns out that on the real line, those regularity conditions are automatic under this constraint, and so we don't need to worry about them. So, for example, the Stieltjes premeasures that we constructed before we began the extension theorem, that is, those premeasures that defined on the Borel field of half-open intervals give the difference of some increasing right continuous function, those are, of course, Radon measures, since the value is certainly finite here. Well, it turns out that that is a complete characterization of all Radon measures on the real line, and that's our theorem right now. Suppose that mu is a Radon measure on the real line, then there exists a non-decreasing right continuous function which is unique up to an additive constant such that the measure is determined on the semi-algebra of half-open intervals generating the Borel sigma field by this formula. So let's prove that. First, let's start with uniqueness. Okay. And for uniqueness, this is a simple function equality. Suppose that we could also write f at b minus f at a as g at b minus g at a for every a and b of this form. Well then, that would tell us that g at b is equal to f at b plus g at a minus f at a. We have total freedom about choosing a and b here, so let's choose a to equal, say, 0. And there's our constant, showing us that g and f differ by a uniform additive constant. So that handles uniqueness. Now how about existence? Well, in the case where the measure is finite, or in fact as long as it's finite from minus infinity up to x for any x, we can simply take f at x to equal the measure of the interval from minus infinity up to x. The reason why this works is as follows. If mu of a set B is finite and A is contained in B, then the measure of the difference between A and B can be computed to be the measure of B minus the measure of A, simply by finite additivity. So we can check that the measure of the interval from A up to B in this finite setting is the same as the measure of the difference between minus infinity up to B and minus infinity up to A, since those two sets are equal. And that is the measure of the interval from minus infinity up to B minus the measure of the interval from minus infinity up to A, which is, by the way we've defined it, f at b minus f at a. So we have a function which satisfies the condition. And we can also check that if x is less than or equal to y, then f at y, which is the measure of the interval from minus infinity up to y, well, that interval contains the interval from minus infinity up to x, since y is bigger than x. And therefore, by monotonicity of the measure, this is greater than or equal to the measure of the interval from minus infinity up to x, which is f at x. So this function is non-decreasing. Now what about right continuity? Well, let's just check. Suppose I have some sequence that decreases to x in the real line. We should think of this not as a sequence, but a sequence of left endpoints of half-open intervals. Then if I take the interval from xn up to, let's say, x1, the first term in this decreasing sequence, that will of course be contained in the interval from xn plus 1 up to x1, because xn plus 1 is less than or equal to xn. Moreover, by the convergence here, we get that the union of the intervals is equal to the interval from the limit up to x1. Well, that means that this sequence of sets increases to the set from x up to x1. And because that set has finite measure, because this is a Radon measure, it follows by what we proved in the proofs over the last few days that this sequence of sets converges in the pseudometric to that one. And therefore, as we saw, that means that the measure of the difference between them converges to 0. But in this finite measure setting, that measure of the difference, as we saw in the last slide, is the difference between the measures of the two sets, and that's equal to f at x1 minus f at x minus f at x1 minus f at xn, and that's equal to f at xn minus f at x. And combining that with that shows that f at xn converges to f at x, which is precisely the statement, because of that decreasing sequence, that f is a right continuous function. And that concludes the proof. In this case, that the measure was finite. Now, I'll just comment that we can redo the entire proof in the more general case that f is not a finite measure by taking the following. For example, we could take f at x to equal the measure of the set from 0 up to x if x is bigger than or equal to 0, and the measure of the set from x up to 0 with a negative sign if x is less than or equal to 0. And that will do the same trick. And you should check that in the finite measure case, this function and the one we defined here differ by an additive constant. So we see that this function that we've just defined, given a Radon measure, is always non-decreasing and right continuous. We saw in lecture 3.1 that if we start with a non-decreasing right continuous function, then it defines a pre-measure on the Borel field, and therefore by the extension theorem, it defines a full-fledged measure on the Borel sigma field. That is, we have a Radon measure, and we therefore have a full characterization of all Radon measures on the real line. We'll explore them a little bit in the next few minutes. But first, let's backtrack a little bit. This argument here used, again, one of the key lemmas in the extension theorem proof about increasing sequences of sets in the finite measure case, implying convergence in the pseudometric. But we didn't actually need that level of heavy machinery here, Just the fact that these increase was already enough to finish the proof here because of the following general theorem that we could have covered much earlier. Suppose that I have a finitely additive measure on a field, then the following are equivalent. That finitely additive measure is actually a pre-measure, and therefore extends to a full measure. And equivalently, given any sequence of sets in the field that increase to a set in the field, the measure of the ANs increases to the measure of the A's. So we really only need to worry about limits of increasing sequences of measurable sets. Moreover, in the finite measure setting, which is where we will spend most of our time in this course, these two statements are also equivalent to these three. We can also consider only decreasing sequences. And just to be clear, decreasing sequences means that AN contains AN plus 1, and that A is equal to the intersection of the ANs. We can also only consider sequences that increase to the full sample space, and we can also consider sequences that only decrease to the empty set. All of those are equivalent characterizations of what it means to be countably additive and therefore extend to a fully fledged measure. So why is that? Well, let's look at the proof of equivalence of a couple of these. So let's start by assuming one, that mu is a pre-measure, meaning that it is countably additive. If indeed we have a sequence of sets that increases, then we do the usual thing and disjointify them and let Bn be An minus 1, with the caveat that B1 is just equal to A1. Then these are disjoint. And we also have that the disjoint union of the first capital N of them is the same as the union of the first capital N A's. But because the A's are increasing, that means that this is just An. And by taking capital N to infinity, the disjoint union of all of the B's is equal to A. Well, therefore, by 1, which is the assumption that mu is actually countably additive, we get that the measure of A is the same as the sum of the measures of the Bn's, which is by definition the limit, as capital N goes to infinity, of the sum up to capital N of the measure of the Bn's. Now, the general assumption here is that mu is finitely additive at least, and so this is the same as the limit as capital N goes to infinity of the measure of the disjoint union of the first n B's, but that is just the same as the measure of An, which is the statement that we wanted to prove. So that implies 2. Now for the converse, that 2 implies 1, we suppose that 2 holds, and we want to show that mu is a pre-measure. So that means we need to start with a sequence of disjoint sets. Let's say B is the disjoint union of some Bn's. Then we simply note, reversing the argument from the previous line, that the disjoint union of the first n of them increases to B. And therefore, by our assumption of property 2 in this case, the measure of that B is equal to the limit of the measure of the disjoint union of the first n of them. And again, using finite additivity of mu, that's the sum of the measures of the Bn's, which is the countable sum that we wanted to show was indeed equal to the measure of B, showing that mu is indeed a pre-measure. The arguments for the equivalence of 3, 4, and 5 with the others are very similar. They just repeatedly involve the additional step, which we used on the last slides, that in the case of finite measure, if A is contained in B, then the measure of B minus A is the measure of B minus the measure of A. This very simple continuity characterization of what it means for a finitely additive measure to actually be a measure will be very useful to us in the coming lectures. Now let's take a moment to introduce some notation we'll be using frequently from now on. In the special case that our Borel measure on the real line is a probability measure, therefore a finite measure and therefore a Radon measure, the function which we defined to give the Stieltjes characterization of the measure has a special name. It is called the cumulative distribution function of the measure. And what we have just proved is that by the Radon measure characterization theorem, Borel probability measures on the real line are completely characterized by their cumulative distribution function, because each Radon measure is totally determined by its non-decreasing right continuous function that defines it. Now for probability measures beyond right continuous and non-decreasing, there are two additional small constraints that come for free. First, by our choice of which additive constant to choose for the function, we have in this case that as x goes to minus infinity, the limit of f at x is equal to the limit of the measure of the interval from minus infinity up to x. But by the continuity theorem that we just proved, since the interval from minus infinity up to x goes down to the empty set, this is equal to the measure of the empty set, which is of course always 0. On the other hand, because we have a probability measure here, if we take x up to infinity, the limit as x goes to plus infinity of f at x is the same as the limit as x goes to infinity of the interval from minus infinity up to x. That interval increases to the whole real line, and so by the continuity result we just proved, this limit converges to the measure of the real line. Because we have a probability measure, that's 1. And so what we see is that if we have any right continuous non-decreasing function which satisfies these two limits, then it is the CDF of a unique Borel probability measure on the real line. And conversely, any Borel probability measure on the real line has a CDF satisfying these conditions. Let's take a look at a few examples of CDFs of probability measures. Among the first probability measures that we introduced were pure point measures. Let's look at an example. Here we have a convex combination of 3 point masses. 1/3 of a mass at 0, 1/9 of a mass at 1, and the remaining portion of 1, 5/9 of a mass at Napier's constant E, 2.71828, etc. So what does the CDF of this Borel probability measure look like? Well, we revert to the definition. So f mu at each x is the measure of the interval from minus infinity up to x. Now if x is less than 0, there's no mass, and so our function is just 0 out here. What about if we're greater than 0? So if we're greater than 0, the interval from minus infinity up to x, closed, contains 0. Until we reach 1, the only point among these three that it contains is 0, and so we have picked up a mass of 1/3 as we cross 0. Now, let's be careful about what happens at 0. That's not exactly determined by the formula unless you squint very hard, but we remember that cumulative distribution functions are always right continuous. That means that the limit has to be at the top there and open at the bottom. Now, when we pass 1, we now have picked up a little more mass. We still have the 1/3 from before, but we pick up an extra 1/9 as we pass 1 and all the way until we get to the next mass. And so we have the following. And then finally, when we get to E, we pick up the rest of the 5/9, taking us all the way to 1 from that point forward. And so that is what the CDF of this measure looks like. This is a pure point mass probability measure, or purely discrete. And therefore, as we see, its CDF is a non-decreasing, right continuous step function. Great. Now let's look at a different example. Here, I've written down a CDF. I've written down a non-decreasing, continuous, and therefore right continuous function, which tends to 0 at -infinity and tends to 1 at +infinity. And therefore, it is the CDF of a probability measure. We can draw it. It looks like that. Now this one has no point mass. Indeed, we can just check that if I take any point in the real line, the measure, under the measure associated to this f of the singleton x0, well, the singleton x0 can be written as a decreasing family of half-open intervals. If I take any x less than x0 and let x tend to x0 from below, then that half-open interval will shrink down to the point x0. And so by the continuity properties on the last slide, I get this. Well, that's the limit as x goes to x0 of f at x0 minus f at x. Now I could write down a piecewise formula for what that difference is, but there's no need because this function f is continuous, which exactly says that that limit is 0, no matter what x0 is. In fact, that's a general principle here that we've proved. If the cumulative distribution function of the probability measure is continuous, then there is no mass at any point. The mass is always distributed over an interval, never at a single point. Now, you probably recognize that this CDF is an important one. This is the CDF of the uniform probability measure on the unit interval, which will play a very important role in much of what we do this year. So we see two diametrically opposed examples here. A purely discrete probability measure, which therefore has a step function as its CDF, as compared to a probability measure that has no point mass anywhere and has a continuous CDF. Now, one could easily cook up examples of probability measures that are a combination of these two, that have some steps and some continuous parts, that would be a convex combination of measures of these two types. It's more complicated than that, however. This continuous CDF is not just continuous, it's also differentiable at almost every point. In fact, it's differentiable except at 2 points. And as we'll see as we go further, that says that this probability measure has a nice density. Now, if you've taken undergraduate probability, you might be left with the false impression that there are only two kinds of probability measures up to combinations. Ones like this, and ones that have a density. That is most definitely not true. So let's look at one more example that, like this example, has a continuous CDF, but is fundamentally different in nature. And that is the devil's staircase, also called the Cantor function. We're going to construct, right now, a continuous, non-decreasing function that rises from 0 up to 1 on the unit interval, and is flat everywhere else, that is also flat pretty much everywhere, which sounds like a paradox. Here's how we do it. We start by constructing the Cantor set, the classic middle thirds Cantor set. That means we start with the unit interval, call that C0, and then we iterate a process to get our new set C. C1 is achieved from C0 by removing the middle third of that interval, leaving us with two intervals, each of length 1/3. Then C2 is achieved from C1 by removing the middle third of each of the intervals, leaving us with 4 intervals, each of length 1/9, and holes of various sizes. And then we repeat that process, cutting out the middle third of each of the intervals that was left. And we keep going. So that defines Cn for each n. And the Cantor set, by the way, which will feature in our next lecture, is the intersection of all of those closed sets. Now we can also define a continuous, non-decreasing function on the real line associated to each of those Cantor set approximants. And here it is. Don't worry about this being defined as an integral, thinking that we haven't done integration theory yet. This is just a plain old Riemann integral from calculus. And this is just a way of saying we're going to do linear interpolation. For example, looking at C1, where we've cut out the middle interval, this formula is designed to make the function be linear from 0 up to there, and then flat at height 1/2, and then linear up to here, and then flat afterward. For C2, this goes linearly up to 1/9, where it has height 1/4, and then linearly here, and then linearly here, and then linearly there. For C3, it staggers in between all of the holes that we made up to that iterant in the construction, and so on down the line. That gives us a sequence of piecewise affine continuous functions that are non-decreasing and all go from 0 up to 1. Now here's the theorem from undergraduate analysis. Because this convergence is sufficiently uniform, that sequence of functions actually converges to a function as n goes to infinity, a function which wiggles between up and flat on smaller and smaller scales. That function is continuous and non-decreasing, and therefore it is a cumulative distribution function of some probability measure. Let's take a look at that function. Here is many iterations of it. So there exists a Borel probability measure on the real line, which has this function as its CDF. And this is a continuous function. So that measure assigns no mass to any point in the real line. Great. But does that mean that it has a density? In fact, this function, f, is differentiable at almost every point in the real line. It is differentiable on all of the flat bits. And the flat bits, that is, the holes in the Cantor set, take up most of the space in the real line, in a sense that we'll get to in the next lecture. So this exists and is 0 almost everywhere. However, the function still increases from 0 up to 1 over the unit interval. It does so by staying flat almost all the time. That seems paradoxical. It's not. It just means that functions can be weirder than our calculus intuition has space for. And it also means that this probability measure cannot have a density. We'll get into the precise definition of density a little bit later, but I want you to keep this example in mind as we go through this material to show that there are lots of different gradations between continuous and discrete. In fact, this is the prime example of a probability measure that is called singular continuous. and we'll get into the precise definition of that later. So we now have a pretty good understanding of radon measures on the real line. We're going to spend the next lecture focusing on one particular radon measure, which is the most important measure that we will use all year, and that is the Lebeg measure.